close your eyes and imagine this. You're standing on solid ground right now, feeling the earth beneath your feet, confident in its stability. But beneath that thin shell of rock you're standing on, hidden from view, exists a world more alien than the surface of Mars. A realm where iron rain falls upward, where rocks flow like honey, where temperatures rival the surface of the sun, and where pressures would compress you to the size of a marble in an instant. This isn't science fiction. This is what lies beneath your feet at this very moment. Journey with me now as we descend into the depths of our planet, peeling back layers of mystery that took humanity centuries to understand and discover what truly hides inside the Earth. Before we begin our descent into Earth's hidden interior, we need to understand why this journey must be one of imagination rather than physical exploration. You might think that with all our technological prowess, with rovers on Mars and probes beyond our solar system, surely we could simply drill down and see what's there. The reality is far more humbling. The deepest hole ever drilled by humanity is the Kola super deep borehole in Russia. For over 2 decades, from 1970 to 1992, Soviet scientists pushed the boundaries of engineering, drilling deeper than anyone had before. They reached 7.6 miles down, 12,262 meters into the Earth's crust. It took them 22 years. The hole is only 9 inches wide at its deepest point. And here's what's remarkable about that achievement. They barely scratched the surface. To put this in perspective, Earth's radius measures roughly 3,959 miles. The Kola borehole penetrated less than 0.2% of that distance. It's as if you tried to understand the composition of an apple by pricking its skin with a needle. The drill never even made it through the crust, let alone reach the mantle beneath. And it wasn't for lack of trying. At those depths, the temperature reached 356 degrees Fahrenheit, far hotter than predicted. The rock became so hot and so plastic that the drill hole kept trying to close behind the drill bit. The equipment couldn't withstand the conditions. The pressure was immense. The heat was unbearable for any material we could engineer. And they were still miles away from the boundary between the crust and mantle, a transition that occurs at roughly 18 to 43 miles beneath the continents. So if we can't drill there, if we can't send probes, if we can't physically observe the interior of our planet, how do we know what's down there? The answer is both elegant and fascinating. We listen. We listen to the Earth itself, to the vibrations that travel through it, to the subtle whispers of earthquakes and the echoes they create. We use physics, mathematics, and careful observation to build a picture of something we can never directly see. And the picture we've assembled is extraordinary. Let's begin our journey at the only layer we truly know through direct observation: the crust, the solid ground beneath your feet, the foundation of mountains, the floor of oceans, the skin of our planet. It seems so permanent, so substantial. But in the grand scheme of Earth's structure, the crust is extraordinarily thin, fragile, a delicate shell separating us from the intense heat and pressure of the world below. There are 2 types of crust, and they're dramatically different from each other. Oceanic crust lies beneath Earth's oceans. It's thin, typically only 3 to 6 miles thick. It's dense, heavy, composed primarily of basaltic rocks rich in iron and magnesium. These are mafic rocks, dark in color, formed from the cooling of lava that erupts at mid-ocean ridges. The oceanic crust is young in geological terms. Most of it is less than 200 million years old. It's constantly being created at spreading centers and destroyed at subduction zones, recycled back into the mantle in an endless cycle. Continental crust is different, thicker, lighter, more complex. It ranges from 18 to 43 miles thick, but beneath major mountain ranges like the Himalayas, it can extend down nearly 70 miles. Continental crust is composed of lighter rocks, rich in silica and aluminum. Granite is the quintessential continental rock, felsic in composition. less dense than its oceanic counterpart, and ancient. Some continental rocks are over 4 billion years old, witnesses to nearly the entire history of our planet. The boundary between the crust and the layer beneath was discovered in 1909 by a Croatian seismologist named Andrija Mohorovičić. He was studying earthquake waves when he noticed something peculiar. Seismic stations farther from an earthquake sometimes detected waves before stations that were closer. This seemed impossible until Mohorovičić realized what was happening. The waves were taking a shortcut. They were diving down into a deeper layer where they could travel much faster, then arcing back up to the surface. The speed increase was so dramatic that even though the path was longer, the travel time was shorter. This boundary became known as the Mohorovičić discontinuity, or simply the MOHO. It marks the transition from crust to mantle. At this boundary, seismic waves suddenly accelerate, jumping from about 4 to 5 miles per second in the lower crust to roughly 5 miles per second in the upper mantle. This change indicates a fundamental shift in composition and density. You're leaving behind the relatively light rocks of the crust and entering a realm of denser, iron-rich minerals. The crust is broken into massive pieces called tectonic plates. These plates float on the layer beneath like rafts on a slowly churning sea. They drift at speeds of just a few inches per year, but over millions of years, this movement reshapes continents, builds mountains, and creates oceans. The plates collide, separate, and slide past each other. Where they meet, earthquakes rupture the ground, volcanoes erupt, mountain ranges rise. The crust, for all its seeming solidity, is in constant motion. But the crust is just the beginning. Beneath it lies something far more mysterious, far more dynamic, and far more massive. Descend past the MOHO and you enter a different world, the mantle. This layer extends from the base of the crust down to a depth of 1,800 miles. It's not hollow, it's not empty space. It's solid rock, but rock under such extreme pressure and temperature that it behaves in ways that seem almost impossible. The mantle makes up 84% of Earth's volume and about 67% of its mass. It's the largest layer by far. If you could somehow extract the mantle and set it aside, what remained, the crust and core combined, would be a tiny fraction of the planet's substance. Understanding the mantle is essential to understanding Earth itself. The rock here is ultramafic, even richer in iron and magnesium than oceanic crust. The dominant rock type is peridotite, a dense, greenish rock composed primarily of the minerals olivine and pyroxene. Near the surface of the mantle, temperatures hover around 1,300 degrees Fahrenheit. As you descend, they climb steadily, reaching approximately 7,200 degrees Fahrenheit at the boundary with the core. Now here's where it gets interesting. Despite these extreme temperatures, the mantle is solid, not liquid, not molten. The immense pressure at these depths, tens of thousands of times greater than atmospheric pressure at Earth's surface, keeps the rock in a solid state. But this isn't solid like a granite countertop. This is solid like cold honey, or like glass that flows imperceptibly over centuries. The mantle is what scientists call a viscous solid. It can flow, but it flows so slowly that you'd never perceive the motion in a human lifetime. The mantle is divided into several distinct regions, each with its own characteristics. The upper mantle extends from the MOHO down to about 410 miles. Here, the pressure is already intense, but not yet extreme. The rock is hot, but still relatively rigid near the top. This uppermost portion, combined with the crust above it, forms what's called the lithosphere, the rigid shell that makes up the tectonic plates. Just below the rigid lithosphere lies a remarkable zone called the asthenosphere. This layer, stretching from roughly 50 to 120 miles beneath the surface, is where the rock becomes plastic, soft enough to flow more easily. The asthenosphere is slightly hotter than the rock above and below it, and this heat combined with pressure conditions, causes partial melting in some regions. About 1 to 2% of the rock here is molten, just enough to lubricate the layer and allow it to deform. This is the layer on which the tectonic plates ride. Without the asthenosphere, plate tectonics as we know it wouldn't exist. The mantle convex. Like water boiling in a pot, hot rock rises from deep within, cools near the surface, and sinks back down. But this isn't rapid boiling, it's glacially slow. The rock might move a few inches per year at most. Yet over millions of years, this convection reshapes the planet. It drives the motion of tectonic plates. It brings heat from the deep interior to the surface. It transports material from the depths to the crust and back again in an endless cycle. At around 410 miles depth, you reach the transition zone. Here, something remarkable happens to the minerals. The pressure has become so intense that olivine, the dominant mineral in the upper mantle, can no longer maintain its crystal structure. The atoms rearrange themselves into a more compact form called wadsleyite. This transformation releases energy, and it's so abrupt that seismic waves show a distinct boundary at this depth. The speed of seismic waves increases suddenly, revealing the change in material. Descend further, to 520 miles down, and the pressure forces another transformation. Wadsleyite converts to ringwoodite, an even denser polymorph of olivine. Same chemical composition, different atomic arrangement. The atoms pack more tightly together, forming a more stable structure under these extreme conditions. We'll return to ringwoodite shortly, because this mineral holds one of Earth's most astonishing secrets. At 660 miles depth, you reach the bottom of the transition zone. Here, the most dramatic transformation yet occurs. Ringwoodite breaks down completely, separating into bridgmanite and ferropericlase. These are fundamentally different minerals with crystal structures that can withstand the even more extreme pressures of the lower mantle. The boundary at 660 miles is so sharp, so distinct, that seismic waves show it clearly. It marks the transition from the upper mantle to the lower mantle. The lower mantle is a different beast entirely. It extends from 660 miles down to 1,800 miles, the boundary with the outer core. The pressure here is staggering, reaching 140 gigapascals at the bottom. That's 1.4 million times atmospheric pressure. The temperature climbs to around 4,000 degrees Fahrenheit. The rock is still solid, but it's so hot and under so much pressure that its properties are unlike anything we experience at the surface. Bridgmanite is the most abundant mineral in this region, and therefore the most abundant mineral in the entire Earth. It makes up about 38% of the planet's volume. Yet until 2014, we had never seen a natural sample of it. It only exists at the extreme pressures of the lower mantle. Bring it to the surface, and it transforms into other minerals immediately. The only reason we finally confirmed its existence was by finding tiny grains of it trapped inside diamonds, brought up from the depths by volcanic eruptions, and protected by the immense strength of their diamond prisons. The lowermost 125 miles of the mantle, the region directly above the core, is called the D double prime layer, written as D double prime. This is perhaps the most mysterious region of the mantle. Seismic waves slow down here in unexpected ways. The temperature gradient is extreme. Chemical interactions with the liquid metal core below create strange effects. And in recent years, scientists have discovered something extraordinary in this layer, something we'll explore in detail later. Ancient structures, massive anomalies, features that challenge our understanding of how Earth works. The mantle is not just a static layer of rock. It's a dynamic system, a heat engine that drives the surface processes we see every day. Volcanoes, earthquakes, mountain building, ocean creation. All of these phenomena are surface expressions of what's happening in the mantle below. The mantle is Earth's engine room, and it's been running, churning, convecting for over 4 billion years. At 1,800 miles beneath the surface, everything changes. Suddenly, dramatically. You've reached the core mantle boundary, and you're about to enter a realm of liquid metal. The outer core is a shell of molten iron and nickel, alloyed with lighter elements like sulfur, oxygen, and silicon. It's roughly 1,400 miles thick, extending from 1,800 miles down to 3,200 miles beneath the surface. And when we say liquid, we mean truly liquid, flowing like water, but far denser and far hotter. How do we know it's liquid? The answer comes from seismic waves, specifically from what doesn't travel through this region. Earthquakes generate two main types of body waves. P waves, or primary waves, are compressional waves that can travel through both solids and liquids. S waves, or secondary waves, are shear waves that can only propagate through solid materials. When a large earthquake occurs on one side of the planet, seismometers on the opposite side detect P waves that have passed through the core, but they don't detect S waves. The S waves simply vanish, blocked by the liquid outer core. This creates what's called the S-wave shadow zone, a region on the opposite side of the Earth from any earthquake where S-waves never arrive. This shadow zone provided some of the earliest evidence that Earth's core is at least partially liquid. The P waves are refracted as they pass through the liquid outer core, bent by the change in material properties, creating a corresponding P-wave shadow zone as well. These shadow zones have been mapped precisely, and they tell us exactly where the boundaries of the outer core lie. The temperature in the outer core is extreme. Estimates put it between 7,200 and 9,000 degrees Fahrenheit. At the top of the outer core, where it meets the mantle, temperatures are around 7,200 degrees. At the bottom, where the outer core meets the solid inner core, they reach perhaps 9,000 degrees. These are temperatures that rival the surface of the sun. Yet the material remains liquid rather than gas because of the immense pressure. At these depths, the pressure is so great that it takes extraordinary temperatures to vaporize metal. But the outer core isn't just sitting there, it's in constant motion. The liquid metal flows, swirls, and churns in complex patterns driven by several forces. Heat escaping from the inner core below creates thermal convection. The cooling and solidification of iron at the inner core boundary releases lighter elements that rise through the outer core. Earth's rotation organizes these flows into columns aligned with the rotation axis, a consequence of the Coriolis effect. The result is a roiling ocean of liquid metal, conducting electricity and generating magnetic fields. This brings us to one of the most important features of the outer core. It's the source of Earth's magnetic field, the invisible shield that protects us from harmful solar radiation and cosmic rays. The mechanism is called the geodynamo, and it's one of the most fascinating processes in our planet. Here's how it works. The outer core is an excellent electrical conductor, being composed primarily of iron and nickel. When electrically conductive fluid moves through a magnetic field, it generates electric currents. These electric currents, in turn, generate their own magnetic fields. If the geometry is right, if the flows are organized properly, these induced magnetic fields can reinforce and sustain the original field. The system becomes self-sustaining, a dynamo. Earth's rotation provides the organization. The Coriolis force causes the convecting fluid to spiral and twist, creating the right geometric conditions for dynamo action. The magnetic field that results is predominantly dipolar, like a giant bar magnet running through Earth's center. But it's far more complex than that simple description suggests. The field has multiple poles and irregularities. It varies over time, and most remarkably, it sometimes completely reverses. Paleomagnetic records, preserved in ancient rocks and ocean floor basalts, show that Earth's magnetic field has reversed its polarity many times throughout history. The north and south magnetic poles swap places. These reversals happen irregularly, sometimes after a few 100,000 years, sometimes after tens of millions of years. The last reversal occurred about 780,000 years ago. We're due for another one, geologically speaking, though when it might occur is impossible to predict. During a reversal, the magnetic field weakens significantly, sometimes to just 10% of its normal strength. The process takes several thousand years to complete. During that time, Earth's protection from solar radiation would be reduced. High-energy particles from the sun would penetrate deeper into the atmosphere. The effects on life would likely be modest, but the effects on our modern technology, which depends on stable magnetic fields for navigation and protection of satellites, could be significant. Recent studies have revealed something unexpected about the outer core. There's a newly discovered structure within it, a donut-shaped region at the top of the outer core, parallel to the equator and found only at low latitudes. This region shows lower seismic velocities than the rest of the liquid outer core. Scientists discovered it by analyzing earthquake waves many hours after the initial quake, looking at the reverberations rather than the first arrivals. The implications are still being studied, but it suggests that the outer core is more complex and heterogeneous than we previously thought. The outer core is also the source of the heat that drives mantle convection. While some of Earth's internal heat is primordial, left over from the planet's formation and from the kinetic energy released when material coalesced under gravity, much of it comes from the core. Radioactive decay of elements like uranium, thorium, and potassium in the mantle generates additional heat. But the core itself, particularly the ongoing process of inner core solidification, releases vast amounts of gravitational energy as heavier elements sink and lighter ones rise. This heat flow from the core is estimated at somewhere between 9 and 15 terawatts. To put that in perspective, that's roughly equal to the total power consumption of modern human civilization. All that energy flowing from the core drives mantle convection, which drives plate tectonics, which shapes the surface we live on. The outer core, hidden and unreachable, is the power source for much of what happens on Earth's surface. Now we reach the heart of our planet, the inner core, a solid sphere of iron and nickel, roughly 1,500 miles across, sitting at the very center of the Earth. This is the deepest, hottest, most extreme environment our planet offers, and it's solid. That last fact seemed impossible when it was first proposed. How could the center of the Earth, the hottest region, be solid when the layer just above it is liquid? The answer, once again, is pressure. At the center of the Earth, the pressure reaches approximately 3.6 million times atmospheric pressure at sea level. This crushing force is so intense that it keeps iron in a solid state despite temperatures that may reach 9,000 to 10,000 degrees Fahrenheit. The melting point of iron increases with pressure. At the center of the Earth, the pressure is so high that the melting point exceeds the actual temperature, and the metal remains solid. The discovery of the inner core is one of the great detective stories in the history of science. Until 1936, scientists believed the Earth's core was a single molten sphere. They had evidence of a liquid region from the behavior of seismic waves, but they assumed it was liquid all the way through. The observations didn't quite fit the theory, but the discrepancies were subtle enough that many scientists didn't pay them much attention. Enter Inge Lehmann, a Danish seismologist working at the Royal Danish Geodetic Institute. Lehmann had been analyzing earthquake records from around the world, and she kept noticing something strange. P waves were appearing in places they shouldn't be, in the shadow zone where they should have been blocked or refracted away by the liquid core. In 1929, a major earthquake near New Zealand provided particularly clear data. P waves had definitely reached seismic stations in the shadow zone. Lehmann had an idea. What if the core wasn't uniform? What if there was a boundary inside the core where the material changed? She proposed that Earth had a solid inner core surrounded by a liquid outer core. P waves could pass through the liquid outer core, reflect off the solid inner core, and reach stations in the shadow zone by taking these reflected paths. The travel times she calculated matched the observations perfectly. In 1936, Lehman published a paper titled simply P', referring to reflected primary waves. In it, she wrote, "We take it that, as before, the Earth consists of a core and a mantle, but that inside the core, there is an inner core in which the velocity is larger than in the outer one." Her hypothesis was met with skepticism at first. Many scientists were reluctant to overturn the accepted model. But as more earthquake data accumulated, as more seismologists examined the evidence, the conclusion became inescapable. Lehman was right. Earth has a solid inner core. The boundary between the inner and outer core is now called the Lehman discontinuity in her honor. It's located about 3,200 miles beneath the surface. At this boundary, seismic waves suddenly accelerate. P wave velocities jump from about 6.2 miles per second in the outer core to about 6.8 miles per second in the inner core. This change confirms the transition from liquid to solid. The inner core is primarily iron, mixed with perhaps 5 to 10% nickel and small amounts of lighter elements. Under the extreme pressures at Earth's center, this iron exists in a form called hexagonal close-packed crystal structure, different from the body-centered cubic structure of iron at lower pressures. The atoms are arranged in a particular geometric pattern that's stable only under these conditions. And here's something remarkable. The inner core is rotating, not at the same rate as the rest of the planet, but slightly faster. The inner core super-rotates, completing one extra revolution relative to the Earth's surface roughly every 400 years. This was predicted by geodynamo models before it was observed, a triumph of theoretical physics. The rotation is driven by magnetic and gravitational interactions with the outer core and mantle. But recent discoveries have added new layers of mystery to the inner core. In 2024 and 2025, scientists analyzing decades of seismic data made a startling announcement. The inner core's rotation is not constant. It has been slowing down. In fact, it may have recently reversed, now rotating backward relative to the surface. And that's not all. The inner core appears to be changing shape. Researchers studying repeating earthquakes, nearly identical seismic events that occur in the same location years apart, noticed subtle differences in the seismic waves that graze the surface of the inner core. The simplest explanation is that the inner core is deforming, its shape changing over time. The boundary between the inner and outer core is not rigid. It's more like jelly, soft enough to flex and bend under the forces acting on it. These changes might be related to how heat escapes from the core, or to chemical interactions at the boundary, or to complex dynamics in the liquid outer core. The implications are still being explored, but one thing is clear. The inner core is far more dynamic than we ever imagined. It's growing on one side and shrinking on the other. It's shifting position. It's responding to forces we're only beginning to understand. There's also evidence of layering within the inner core itself. Some studies suggest there's an innermost inner core, a region at the very center with different properties from the surrounding material. The crystal orientations appear to change. The seismic velocities vary. If this innermost core exists, it might represent material from the earliest stages of Earth's formation, primordial iron that has remained at the center for over 4 billion years. The inner core is still growing. Iron from the liquid outer core continuously solidifies onto the inner core's surface, adding roughly 0.04 inches per year to its radius. This may not sound like much, but over millions of years, it represents significant growth. When Earth first formed, there may have been no inner core at all. The entire core was liquid. As the planet cooled, iron began to crystallize at the center, and the inner core has been growing ever since. This crystallization process is actually one of the main power sources for the geodynamo. When iron solidifies, it releases latent heat, the same way water releases heat when it freezes. It also releases gravitational energy as the heavy iron sinks and lighter elements are excluded from the crystal and rise upward. This energy drives convection in the outer core, which sustains the magnetic field. Without the inner core, Earth's magnetic field might not exist. Now we turn to one of the most unexpected discoveries in recent decades, something hiding in Earth's interior that completely changes how we understand our planet's water cycle. There's water in the mantle. Not a little bit, not trace amounts, potentially more water than in all the oceans on Earth's surface combined. This sounds impossible. We just discussed how hot the mantle is, how the rock is solid, how the pressure is immense. How could water exist there? The answer is that it's not water as we know it. It's not liquid H2O, pooled in underground caverns. It's water chemically bound within the crystal structure of minerals, stored as hydroxide ions, hydrogen and oxygen atoms, locked into the atomic framework of rock. The key mineral is ringwoodite, one of the high-pressure forms of olivine that exists in the mantle transition zone between 250 and 410 miles beneath the surface. Ringwoodite has a remarkable property. Its crystal structure can incorporate water, replacing some magnesium ions and oxide ions with hydroxide ions. The mineral acts like a sponge, soaking up water and holding it in its crystal lattice. Laboratory experiments have shown that ringwoodite can contain up to 2.5 to 3% water by weight under mantle conditions. That might not sound like much, but consider the volume of the transition zone. If even 1% of the ringwoodite in the transition zone contains water, that's enough to equal 2 to 3 times the total water in all of Earth's oceans. The numbers are staggering. For years, this was purely theoretical. Scientists knew ringwoodite could hold water. They'd synthesized it in laboratories at high pressure and temperature, reacting olivine with water and confirming the uptake. But did natural ringwoodite in Earth's mantle actually contain water? Or was the transition zone dry, the water content negligible? In 2014, everything changed. A team of researchers led by Graham Pearson at the University of Alberta published a paper in the journal Nature that sent shockwaves through the geological community. They'd found a diamond, not just any diamond, but a small, brown, commercially worthless specimen from Brazil. This diamond had formed deep in the earth and been brought to the surface by a violent volcanic eruption called a kimberlite, and trapped inside it was a tiny inclusion of ringwoodite. Diamonds are extraordinary capsules for preserving deep earth material. They form under immense pressure and have incredible strength. When a diamond forms around an inclusion and is then carried rapidly to the surface, the inclusion remains under pressure, protected by the diamond's rigid structure. The ringwoodite in this diamond couldn't transform back into lower pressure minerals. It was frozen in place, a snapshot of deep mantle conditions. The researchers analyzed the inclusion and found it contained about 1.5% water by weight. This was the first direct evidence, the smoking gun, that the mantle transition zone contains significant water. Not everywhere, perhaps. The diamond might have sampled an unusually water-rich region, but at least locally, in at least some parts of the transition zone, there's water. Lots of it. How does water get down there? The answer is plate tectonics. When oceanic crust forms at mid-ocean ridges, it reacts with seawater. Water penetrates into the rock, altering minerals and becoming chemically bound. This hydrated oceanic crust then spreads across the ocean floor until it reaches a subduction zone where it descends back into the mantle. As it sinks, the rock heats up and different minerals break down at different depths, releasing their water. But some minerals hold onto water to extreme depths. They carry it hundreds of miles down into the transition zone. There, at around 400 miles depth, the rock encounters ringwoodite. The water released from other minerals is absorbed by the ringwoodite, which can hold far more water than the minerals in the upper mantle or lower mantle. The transition zone acts as a reservoir, a storage layer for water transported from the surface. Seismic studies support this picture. Researchers have detected regions of partial melting at the top of the transition zone, right where water-rich ringwoodite would encounter the base of the upper mantle. When ringwoodite tries to move upward into the upper mantle, it transforms into wadsleyite, which can't hold as much water. The excess water is released, and this water lowers the melting point of the surrounding rock, causing partial melting. Seismic waves slow down in these partially molten regions, and that's exactly what observations show. But water doesn't just enter the transition zone, it also leaves. When ringwoodite is pushed deeper into the lower mantle, it breaks down into bridgemanite and ferropericlase. These minerals can hold almost no water compared to ringwoodite. The water is forcibly expelled. This creates what's called dehydration melting, where the release of water causes the rock to partially melt at the boundary between the transition zone and lower mantle. This melt might be the source of some deep mantle plumes. Recent studies using seismic tomography, mineral physics, and viscosity measurements suggest that the mantle transition zone globally contains water equivalent to roughly one Earth ocean, not uniformly distributed, but on average across the entire transition zone. Some regions are wetter, near subduction zones where hydrated slabs descend. Some regions are drier, but the average is surprisingly high. This has profound implications for how we understand Earth. The water cycle isn't just about evaporation, rain, rivers, and oceans. It's a deep cycle that extends hundreds of miles into the interior. Water from the surface is carried down by subducting plates, stored in the transition zone, released through volcanic activity and mantle upwelling, and returned to the surface over millions of years. Earth's interior and surface are connected in ways we're only beginning to appreciate. It also raises questions about Earth's formation and evolution. Where did all this water come from originally? Was Earth born wet, accreting from water-bearing materials in the early solar system? Or did water arrive later, delivered by comets and asteroids? The presence of water in the deep mantle suggests that at least some of it was incorporated during Earth's formation, that the planet was never entirely dry. And it changes how we think about mantle dynamics. Water dramatically lowers the viscosity of minerals, making them flow more easily. A water-rich transition zone would be weaker, more plastic, potentially affecting how the mantle convects and how tectonic plates move. Understanding the distribution of water in the mantle is crucial for understanding the forces that shape our planet's surface. Beneath Africa and beneath the Pacific Ocean, in the lowermost reaches of the mantle, sit two enormous structures unlike anything else on Earth. They're called large low shear velocity provinces, abbreviated as LLSVPS, but often referred to more colloquially as blobs. They're continent-sized masses of rock that seismic waves travel through more slowly than the surrounding mantle. And they may be billions of years old, ancient relics from Earth's earliest days. Each LLSVP is staggering in size. They rise up to 600 to 1,000 miles above the core mantle boundary. They extend thousands of miles laterally. Together, they occupy perhaps 3 to 9% of Earth's volume. If you could somehow extract them and place them on the surface, each would cover an area larger than North America. The African LLSVP sits beneath the African continent and the Atlantic Ocean to its west. The Pacific LLSVP occupies a vast region of the deep mantle beneath the Pacific Ocean. They're antipodal, located on opposite sides of the Earth, and they're remarkably stable. Despite the constant churning of mantle convection, Despite billions of years of change, these structures have remained largely in place. How do we know they exist? Through seismic tomography, a technique that's essentially a CAT scan of Earth's interior. When earthquakes occur, they send out seismic waves that travel through the planet. These waves speed up or slow down, depending on the properties of the material they're passing through. Hotter rock, less dense rock, partially molten rock, all transmit seismic waves more slowly than colder, denser, solid rock. By analyzing thousands of earthquakes and millions of seismic wave travel times from stations all over the world, scientists can create three-dimensional maps of seismic velocity variations within Earth. Regions where waves travel faster appear in red on these maps. Regions where they travel slower appear in blue. And when you look at the lowermost mantle in these tomographic images, the LLSVPS stand out clearly. Massive blue blobs sitting on the core mantle boundary. But what are they? That's where the mystery deepens. Several hypotheses have been proposed, each with different implications for Earth's history and evolution. The first hypothesis is that they're purely thermal anomalies, regions of hotter rock that rise from the core mantle boundary. Hotter rock is less dense and transmits seismic waves more slowly. The problem with this explanation is that thermal anomalies should rise. Hot rock is buoyant. It shouldn't sit stably at the base of the mantle for billions of years. Geodynamic models predict that purely thermal plumes would be long and narrow, not broad and blob-like. The LLSVPS don't fit this picture. The second hypothesis is that they're compositionally different from the surrounding mantle. They're made of rock with a different chemical makeup, denser than normal mantle material. This density difference could anchor them at the core mantle boundary despite being hot. They'd be thermochemical structures, both hot and compositionally distinct. But where would this different rock come from? One possibility is that it's primordial material, left over from Earth's formation. When the planet was young, it may have differentiated incompletely. Dense, iron-rich materials sank toward the core, but perhaps not all of them made it. Perhaps some dense, primitive material got trapped at the base of the mantle and has been sitting there ever since. The LLSVPS might be relics of the magma ocean that covered Earth's surface over 4 billion years ago. Another possibility is that the SVPS are graveyards of oceanic crust. For billions of years, oceanic plates have been subducting into the mantle, sinking down toward the core mantle boundary. This oceanic crust, called basalt, is denser than normal mantle rock. When it reaches the deep mantle, it might pile up, unable to sink into the core, but too dense to rise. Over eons, enough subducted crust could accumulate to form the massive piles we see today. A third possibility, proposed more recently, involves the formation of the moon. The giant impact hypothesis suggests that early in Earth's history, a Mars-sized body called Theia collided with the proto-Earth. This collision was so violent that it vaporized rock, created an ocean of magma, and flung debris into orbit that eventually coalesced to form the moon. Some researchers propose that the LLSVPS are remnants of Theia itself, dense material from the impactor that sank to the core mantle boundary and has remained there ever since. Recent studies have revealed that the two LLSVPS are not identical. The African LLSVP rises about 600 miles higher than the Pacific LLSVP. This difference suggests that they may have different densities or compositions. The African SVP appears to be less dense and therefore less stable, potentially more buoyant. The Pacific LLSVPP seems denser and more firmly anchored. These differences might reflect different origins or different evolutionary histories. The LLSVPS also have sharp boundaries. Early tomographic images were fuzzy, and it was unclear whether the structures had distinct edges or gradual transitions. But more recent studies using seismic waves that reflect off these structures have shown that the boundaries are remarkably sharp. This suggests a real compositional contrast, not just a thermal gradient. Surrounding the LSVPS are regions of faster than average seismic velocities. These are thought to be subducted slabs, ancient oceanic crust that has sunk to the core mantle boundary and now rests there, forming what are called slab graveyards. The geometry makes sense. Cold, dense slabs sink to the bottom of the mantle and accumulate around the edges of the LSVPS, unable to penetrate into the denser material of the blobs themselves. The LSVPS appear to be the source regions for mantle plumes, upwellings of hot rock that rise through the mantle and create hotspot volcanism at the surface. Places like Hawaii, Iceland, Yellowstone, all have been linked to plumes that originate near the LSVPS. The hot, potentially partially molten rock at the edges of the LSVPS may be generating these plumes, sending tendrils of hot material up through the mantle over millions of years. At the very base of the mantle, right on top of the core mantle boundary, there's another set of mysterious structures called ultra-low velocity zones, or ULVZs. These are much smaller than the LSVPS, typically just a few miles thick, but they're even more anomalous. Seismic waves slow down dramatically when passing through ULVZs by as much as 10 to 30%. This extreme reduction in velocity suggests that the material in ULVZs might be partially molten or chemically very different from normal mantle rock, or both. ULVZs are often found near the edges of the LSVPS, which might mean they're related. Perhaps the LSVPS are generating these small pockets of melt through chemical reactions with the iron in the outer core. Perhaps ULVZs are fragments of the LSVPs that have broken off. The relationship is still being investigated. One intriguing recent hypothesis suggests that the LSVPS are enriched in ferric iron, Fe3+, in a form of bridgemanite that can incorporate large amounts of iron. This Fe3+ rich bridgemanite would be denser than normal bridgemanite, which could explain why the LSVPS remains stable at the core mantle boundary. It would also explain the seismic velocity reductions, because Fe3+ rich bridgemanite transmits seismic waves more slowly than normal bridgemanite. The story of the LSVPS is still being written. New observations continue to reveal surprising details. Their existence challenges our simple models of how the mantle convects. They suggest that Earth's interior is more complex, more heterogeneous, and potentially more ancient than we imagined. They might be among the oldest structures on the planet, witnesses to events that occurred over 4 billion years ago. At the surface, minerals are constrained by relatively modest conditions. Pressures rarely exceed a few thousand atmospheres. Temperatures stay below a few hundred degrees Celsius, except in volcanic regions. The minerals we find in surface rocks, quartz, feldspar, mica, calcite, are stable under these gentle conditions, but descend into Earth's interior, and everything changes. The pressure climbs to millions of atmospheres. Temperatures reach thousands of degrees. Under these extreme conditions, atoms can pack together in ways that would be impossible at the surface. New minerals form, minerals that exist only in the deep earth, with properties we can barely imagine. Bridgemanite is the champion of high-pressure minerals, not because it's the most exotic, but because it's so important. As we've discussed, bridgemanite is the most abundant mineral in Earth, making up about 38% of the planet's volume. It's a magnesium silicate, MgSiO3 with a structure called perovskite. The atoms are arranged in a three-dimensional framework, with silicon ions in octahedral coordination surrounded by oxygen, and magnesium ions in the gaps. This structure can incorporate other elements. Iron can substitute for magnesium. Aluminum can replace silicon. Ferric iron, Fe3+, can be incorporated in remarkable quantities. The flexibility of the structure means bridgmanite can hold trace elements, potentially serving as a reservoir for incompatible elements that don't fit well in other mantle minerals. Bridgmanite only exists at pressures above about 24 gigapascals, which corresponds to depths below roughly 410 miles. At lower pressures, it transforms into other minerals. Bring bridgmanite to the surface, and it instantly converts to a mixture of other phases. This is why, despite being the most abundant mineral on Earth, we had never seen a natural sample until scientists found tiny grains trapped inside diamonds. But bridgmanite isn't the deepest mineral. At the base of the mantle, in the D layer where pressures exceed 120 gigapascals and temperatures reach 4,000 degrees Fahrenheit, bridgmanite undergoes one final transformation. Its atoms rearrange into an even more compact structure called post-perovskite. Post-perovskite was discovered in 2004, and the discovery was revolutionary. Scientists had been puzzled by seismic observations in the D layer for decades. There were reflections, sharp boundaries, velocity changes that didn't fit the expected behavior of bridgmanite. Then, researchers performed high-pressure experiments in diamond anvil cells, compressing bridgmanite to extreme conditions and heating it with lasers. At around 125 gigapascals, the bridgmanite suddenly transformed into a new phase with a different crystal structure. Post-perovskite has a layered structure with sheets of silicon-oxygen octahedra separated by layers of magnesium ions. This structure is more stable at extreme pressures, and it has different seismic properties than bridgmanite. P waves and S waves travel through it at different speeds. The discovery of post-perovskite explained many of the D layer's puzzling features. The sharp seismic reflections were boundaries between bridgmanite and post-perovskite. The velocity variations were due to temperature and pressure, affecting where the transformation occurred. The transformation from bridgmanite to post-perovskite is sensitive to temperature and composition. Small differences in temperature or iron content can shift the boundary by tens of miles vertically. This means that the D layer is heterogeneous, with patches of bridgmanite and post-perovskite coexisting, their boundaries shifting as the mantle convects and temperatures fluctuate. Other minerals dominate different regions of the mantle. In the transition zone, alongside wadsleyite and ringwoodite, there's a calcium-bearing phase called majorite, a type of garnet that exists only at high pressure. Majorite can incorporate many elements and might play a role in transporting incompatible elements from the upper mantle to the lower mantle. At the very top of the lower mantle, just below the transition zone, calcium silicate perovskite appears. This mineral, recently named Davemaoite after a prominent geophysicist, has a structure similar to bridgmanite, but with calcium instead of magnesium. It makes up about 5 to 10% of the lower mantle. Like bridgmanite, Davemaoite cannot be preserved at the surface except when trapped in diamonds. Ferropericlase is another key lower mantle mineral, an iron-magnesium oxide that forms alongside bridgmanite when ringwoodite breaks down at 660 miles depth. Ferropericlase makes up perhaps 20% of the lower mantle. At pressures above 70 gigapascals, iron in ferropericlase undergoes a spin transition, changing its magnetic properties. This affects the mineral's density and seismic velocities, potentially contributing to some of the complexity observed in the deep mantle. There are likely other minerals we haven't yet discovered or characterized. The conditions in Earth's core mantle boundary region are so extreme that we can barely recreate them in laboratories. Diamond anvil cells can achieve the necessary pressures, but heating samples to thousands of degrees while maintaining those pressures is extraordinarily difficult. Experiments are pushing the boundaries of what's possible, but there are limits to what we can observe. One mineral that has garnered recent attention is iron oxides at ultra-high pressures. In the D layer, iron oxide might exist in unusual forms that are stable only under those conditions. These oxides could react with silicates, creating unique phases. Some researchers have proposed that Fe3 plus rich materials form through redox reactions with the metallic iron in the core, a process that could generate oxygen and affect the oxidation state of the lowermost mantle. Diamond formation itself is a process that occurs in the deep mantle. While most gem-quality diamonds form at depths of 90 to 120 miles beneath the surface in the upper mantle, some diamonds originate from much greater depths. These super-deep diamonds, formed in the transition zone or even the lower mantle, contain inclusions that provide our only direct samples of deep earth materials. Ringwoodite, bridgemanite, davimawete, all have been found as tiny inclusions in these diamonds, precious capsules of information about conditions hundreds of miles below the surface. The minerals in Earth's interior are not just academic curiosities. They control how the mantle convects, how heat is transported, how chemical elements are distributed, the viscosity of the mantle, which determines how easily it flows, depends on the properties of minerals under extreme conditions. The seismic velocities we use to image Earth's interior depend on mineral structures. The phase transformations that create seismic discontinuities, like the 410-mile and 660-mile boundaries, are expressions of minerals changing forms under pressure. Understanding these minerals requires combining observations, experiments, and theory. We use seismic data to constrain what minerals must be present at different depths. We perform laboratory experiments to determine how those minerals behave under extreme conditions. We use quantum mechanical calculations to predict crystal structures and properties at pressures and temperatures beyond what our experiments can reach. All of these approaches together give us a picture of the exotic chemistry hiding in Earth's depths. Earth is not a cold, dead rock floating in space. It's a heat engine, constantly dissipating energy generated in its interior. This heat drives almost everything that happens on our planet. Plate tectonics, volcanism, mountain building, the formation of the atmosphere and oceans, even the conditions that make life possible. Understanding where this heat comes from and how it flows is essential to understanding Earth itself. The total heat flow from Earth's interior to its surface is estimated at roughly 47 terawatts. That's 47 trillion watts, about 3 times the total power consumption of human civilization. This energy is constantly radiating away, mostly through the ocean floor where the crust is thin, but also through continents and volcanic regions. If this heat weren't being replaced, Earth would cool and solidify in a few billion years. So where does the energy come from? There are 3 main sources of Earth's internal heat. The first is primordial heat, left over from the planet's formation. When Earth formed 4.5 billion years ago, countless smaller bodies, planetesimals, collided and coalesced under gravity. Each impact released kinetic energy as heat. The larger the impact, the more heat generated. The collision with Theia that formed the moon released enough energy to melt the entire planet, creating a magma ocean that covered the surface to depths of hundreds of miles. This early Earth was searingly hot. The surface was molten rock. The interior was a chaotic mix of silicates and metals, slowly differentiating as heavier elements sank toward the center. As the planet cooled, the surface solidified into a crust, but the interior remained hot. That primordial heat is still there, still working its way out. Estimates suggest that about 20% of Earth's current heat flow comes from this ancient energy. The second source is radioactive decay. Several elements in Earth's crust and mantle are radioactive, meaning their atomic nuclei are unstable and spontaneously decay into other elements, releasing energy in the process. The main heat-producing isotopes are uranium-238, uranium-235, thorium-232, and potassium-40. These elements are concentrated in the crust and upper mantle, particularly in continental crust. When a uranium or thorium atom decays, it releases alpha particles and gamma rays. These high-energy particles collide with surrounding atoms, transferring their energy as heat. The decay process is slow, individual atoms taking millions or billions of years to decay. But there are so many radioactive atoms in Earth that the total energy released is substantial. Radioactive decay is thought to contribute roughly 50 to 80% of Earth's current heat flow. The third source is gravitational energy from the core. As Earth cools, iron in the liquid outer core crystallizes onto the solid inner core. This process releases latent heat, just like water releases heat when it freezes. Additionally, when iron solidifies, it excludes lighter elements that don't fit in the crystal structure. These lighter elements, oxygen, sulfur, silicon, rise through the outer core, releasing gravitational potential energy. This ongoing crystallization has been happening for billions of years and will continue for billions more. The energy released drives convection in the outer core, which generates Earth's magnetic field. Heat flows from the core to the mantle through conduction across the core-mantle boundary. The temperature difference between the core at 7,200 to 9,000 degrees Fahrenheit and the lowermost mantle at 4,000 to 5,400 degrees drives this heat transfer. The rate depends on the thermal conductivity of the mantle rocks at the boundary. Recent studies suggest the heat flux from the core is around 10 to 15 terawatts. In the mantle, heat is transported by convection. Hot rock near the core-mantle boundary is less dense than cooler rock above it. This density difference creates buoyancy. The hot rock rises, moving upward through the mantle over millions of years. As it rises, it cools by transferring heat to its surroundings. Eventually, it reaches the upper mantle or even the base of the lithosphere, where it loses heat more rapidly. Now cooler and denser, it sinks back down, completing the convection cycle. Mantle convection is complex. It's not a simple boiling pot with hot plumes rising uniformly and cold downwellings sinking uniformly. The mantle has layering, with the transition zone acting as a potential barrier to flow. Some convection cells might be confined to the upper mantle. Others might extend through the entire mantle from core to crust. The presence of the LSVPS, the effects of plate tectonics, the variations in composition and temperature, all create three-dimensional patterns of flow that are extraordinarily complicated. Plumes are one manifestation of mantle convection. These are narrow upwellings of hot rock that rise from the core mantle boundary, possibly originating at the edges of the LSVPS. As a plume rises, the pressure decreases and the rock begins to melt, generating magma. If the plume reaches the surface, it creates a hotspot, a region of volcanism that's not associated with plate boundaries. Hawaii, Iceland, Yellowstone, all are thought to be hotspots fed by mantle plumes. Subduction zones are the complementary downwellings. Cold, dense oceanic lithosphere sinks into the mantle at trenches, pulling more lithosphere behind it in a process that drives plate motion. The subducting slabs descend through the upper mantle. Some stall at the 660-mile discontinuity, accumulating there. Others penetrate into the lower mantle and sink all the way to the core mantle boundary. The fate of subducted slabs is one of the big questions in geodynamics. Heat also escapes through the lithosphere by conduction. The rigid plates act as thermal boundary layers, insulating the hot mantle from the cold surface. Heat flows through the lithosphere slowly, by conduction alone. But at mid-ocean ridges, where new lithosphere is created, hot mantle rock rises close to the surface and cools rapidly, releasing large amounts of heat. At subduction zones, cold lithosphere carries heat back down into the mantle. The balance between heat loss at ridges and heat input from below determines the long-term evolution of Earth's temperature. Volcanic activity is a direct manifestation of Earth's internal heat. Magma generated in the mantle or crust rises to the surface and erupts, bringing heat and materials from depth. The scale of volcanism has varied over Earth's history. In the past, massive volcanic provinces erupted millions of cubic miles of lava, covering vast areas. These flood basalts might be linked to the arrival of mantle plumes at the base of the lithosphere. Today, volcanic activity is concentrated at plate boundaries and hotspots, but it continues to reshape the surface. The geothermal gradient, the rate at which temperature increases with depth, varies depending on tectonic setting. In old, stable continental crust, the gradient might be around 15 to 20 degrees Fahrenheit per mile. In tectonically active regions, near subduction zones or mid-ocean ridges, the gradient is much steeper. This variation reflects differences in heat flow and in the thermal properties of the rocks. Earth's heat engine is running down, very slowly. The planet is losing more heat than is being generated, so the interior is gradually cooling. Models suggest Earth's average temperature has decreased by, perhaps, a few hundred degrees over the past 4 billion years. But the process is so slow that it will take billions more years before Earth cools enough for plate tectonics to cease, for volcanism to stop, for the magnetic field to die. This gradual cooling has profound implications. The inner core is growing. The outer core is slowly solidifying. Mantle convection is weakening. Tectonic activity was probably more vigorous in the past and will be less vigorous in the future. Earth's evolution is a long, slow transition from a hot, active planet to a cold, dead one. We're living in a middle stage where the heat engine is still running strong, but it won't last forever. We've discussed what's inside Earth in great detail: layers, structures, temperatures, pressures, minerals. But how do we know any of this? How can scientists make such specific claims about a place no human has ever been? A place we can't see, can't touch, can't directly sample? The answer is seismology, the study of earthquakes and the seismic waves they generate. These waves that travel through Earth's interior, and by analyzing how they propagate, how they're affected by the materials they pass through, we can reconstruct the structure of the deep Earth with remarkable precision. There are two main types of seismic body waves. P waves, or primary waves, are compressional waves. They work like sound waves, compressing and expanding the material as they pass through. P waves can travel through solids, liquids, and gases. They're the fastest seismic waves, traveling at speeds of 3 to 8 miles per second, depending on the material. Because they arrive first at seismic stations, they're called primary. S waves, or secondary waves, are shear waves. They move material perpendicular to the direction of wave propagation, like shaking a rope up and down. S waves can only travel through solids. Liquids and gases can't sustain shear stress. So S waves stop when they encounter liquid. They're slower than P waves, traveling at 2 to 5 miles per second. They arrive second at seismic stations, hence the name secondary. When an earthquake occurs, it generates both P waves and S waves that radiate outward in all directions. Networks of seismometers around the world detect these waves. By comparing the arrival times at different stations, scientists can determine where the earthquake occurred and how deep it was. But more importantly, they can learn about the material the waves traveled through. Seismic waves don't travel in straight lines through Earth. They bend or refract whenever they encounter a boundary between materials with different seismic velocities. This is similar to how light bends when it passes from air into water. The bending follows Snell's law, a mathematical relationship that describes refraction. Because Earth's interior has layers with different properties, seismic waves follow curved paths, bending toward regions of higher velocity. This refraction creates shadow zones, regions on Earth's surface where certain waves don't arrive after an earthquake. The S-wave shadow zone on the opposite side of the planet from an earthquake told scientists that part of Earth's interior is liquid. The P-wave shadow zone, with its characteristic size and shape, revealed the size of the core. Seismic waves also reflect off boundaries, just like sound waves echo off walls. When waves encounter a sharp change in properties, some of the energy bounces back. Scientists have detected reflections from the 410-mile discontinuity, the 660-mile discontinuity, the core mantle boundary, and the boundary between the outer and inner core. The strength and timing of these reflections provide information about the nature of the boundaries. Seismic tomography takes this further. Instead of just looking at direct waves and simple reflections, tomography analyzes thousands of earthquake records from hundreds of stations, looking at every wave path imaginable. By comparing observed travel times with expected travel times based on a reference model, scientists can identify regions where waves travel faster or slower than average. Faster waves indicate cooler, denser rock. Slower waves indicate hotter, less dense, or partially molten rock. The result is a three-dimensional map of seismic velocity variations throughout Earth's interior. These maps reveal mantle plumes, subducting slabs, the LLLLSVPBS, and countless other structures. They show how the mantle convects, where hot material rises and cold material sinks. They're Earth's CT scans, revealing internal anatomy in stunning detail. But seismology isn't the only tool. Laboratory experiments are crucial. Scientists recreate the extreme conditions of Earth's interior using diamond anvil cells, devices that squeeze tiny samples between two diamonds, generating pressures of millions of atmospheres. Lasers heat the samples to thousands of degrees. X-ray beams probe the structure, revealing what minerals form and how their properties change. These experiments tell us what minerals should exist at different depths. They measure seismic velocities of minerals under pressure and temperature. They determine phase transitions, the pressures and temperatures where one mineral transforms into another. Without lab experiments, we couldn't interpret seismic data. We wouldn't know what seismic velocities correspond to what materials. Computational modeling is another essential tool. Scientists use supercomputers to simulate mantle convection, core dynamics, the geodynamo, mineral behavior at extreme conditions. These simulations test hypotheses. If you assume certain conditions, certain compositions, what do the models predict? Do those predictions match observations? If not, the assumptions need revision. Mineral physics combines experiments with theory. Researchers use quantum mechanics to calculate the properties of minerals at pressures and temperatures beyond what experiments can reach. These calculations predict crystal structures, elastic properties, how atoms will rearrange under extreme conditions. The predictions can then be tested experimentally when possible, or compared with seismic observations. Gravitational and magnetic field measurements provide additional constraints. Earth's gravity field varies slightly across the surface, reflecting variations in mass distribution within the planet. The geoid, the shape of the gravity equipotential surface, has bumps and dips that tell us about density variations in the mantle and core. Satellite missions like GRACE have mapped Earth's gravity field with extraordinary precision. Earth's magnetic field variations, both in space and time, reveal information about the outer core. The field changes on timescales from years to millennia. By studying these changes, scientists can infer patterns of flow in the outer core, test geodynamo models, and learn about the properties of liquid iron under extreme conditions. Chemical analysis of volcanic rocks provides clues about mantle composition. When magma erupts, it brings material from depth. By analyzing the isotopic ratios and trace element concentrations in these rocks, geochemists can determine where the magma originated, what it melted from, how it evolved on its way to the surface. Some volcanic rocks contain xenoliths, chunks of mantle rock brought up accidentally. These are precious direct samples. Meteorites also provide information. Primitive meteorites, called chondrites, are thought to represent the material from which Earth formed. By analyzing their composition, we can estimate what Earth's bulk composition should be. Iron meteorites are thought to be fragments of the metallic cores of destroyed planetesimals, giving us insight into what Earth's core might be like. Even the tides play a role. Earth deforms slightly under the gravitational pull of the Moon and Sun. The amount of deformation depends on Earth's internal structure. By measuring how Earth responds to tidal forces, scientists constrain the properties of the interior, particularly the mantle's viscosity and the core's density. All these methods together, seismology, experiments, modeling, chemistry, gravity, magnetism, have given us a detailed picture of Earth's interior. The picture is incomplete. There are still mysteries, still questions. But what we've learned is remarkable. From the thin crust, to the churning mantle, to the liquid outer core, to the solid inner core at the center, we've mapped a world we can never visit. Science is never finished. Each answer raises new questions. Each discovery reveals new mysteries. The study of Earth's interior is no exception. In recent years, observations and experiments have challenged our understanding, forcing us to reconsider what we thought we knew. The inner core's rotation changes are among the most surprising recent discoveries. For decades, scientists knew the inner core rotates faster than the rest of the planet. This superrotation was predicted theoretically and observed seismically. But in 2024, researchers analyzing decades of earthquake data from repeating events announced that the rotation is not constant. It has slowed down and may have reversed. This was unexpected. The inner core is coupled to the outer core through magnetic and gravitational forces, and to the mantle through gravity. Changes in one part of the system affect the others. A slowdown or reversal of inner core rotation might relate to changes in the geodynamo, to variations in mantle convection, or to complex interactions we don't yet understand. The implications are still being explored. Another recent discovery is that the inner core is changing shape. Seismic waves that graze the inner core's surface show subtle variations over time that can best be explained by deformation at the inner-outer core boundary. This boundary is not rigid, it's viscous, like jelly, soft enough to flex under stress. The inner core might be bulging in some places and contracting in others, possibly due to uneven crystallization or thermal effects. There's also growing evidence for an innermost inner core, a distinct region at the very center with different properties from the outer part of the inner core. Seismic waves show anisotropy, directional dependence, in how they travel through the inner core. In the outer part, the fastest wave direction is roughly north-south. In the innermost core, it might be east-west. This suggests a different crystal orientation, or even a different phase of iron. The discovery of a donut-shaped region in the outer core is another recent surprise. This structure, found only at low latitudes and parallel to the equator, shows slower seismic velocities than the rest of the outer core. It was discovered by analyzing seismic waves many hours after earthquakes, looking at the coda, the later arriving reverberations. The structure's origin and significance are still being investigated. Mantle heterogeneity is proving to be more complex than expected. The LSVPS are not uniform blobs. They have internal structure, layers, sharp boundaries in some places, and gradual transitions in others. The African LSVP is taller and possibly less dense than the Pacific LSVP, suggesting they have different compositions or thermal states. Ultra-low velocity zones at the base of the mantle are more numerous and more variable than previously thought. Water in the mantle is another area of active research. The discovery of water-rich ringwoodite in 2014 was groundbreaking, but many questions remain. How much water is in the transition zone globally? How does it vary by region? How does water affect mantle viscosity, convection, and melting? How does the deep water cycle connect to the surface water cycle over geological time? Post-perovskite's behavior is still being studied. The transition from bridgemanite to post-perovskite depends on temperature, pressure, and composition in complex ways. The boundary can be smeared out over tens of miles or sharp over just a few miles. Understanding this transition is crucial for interpreting seismic observations in the D layer and for understanding heat flow from the core. Chemical interactions between the core and mantle are another frontier. Iron from the core can react with silicates in the mantle, creating iron-rich materials. Oxygen from the mantle might dissolve into the outer core. These reactions could affect the oxidation state of the lowermost mantle, the chemistry of the outer core, and the generation of the magnetic field. The age and growth rate of the inner core remain uncertain. Current estimates suggest the inner core began forming between 500 million and 1.5 billion years ago, but pinning down the exact timing is difficult. The growth rate depends on how fast heat escapes from the core, which depends on mantle dynamics and the thermal conductivity of the core-mantle boundary. Better understanding the inner core's history will help us understand the evolution of Earth's magnetic field. The origin of the LSVPS is still debated. Are they primordial material from Earth's formation? Are they accumulated, subducted crust? Are they remnants of the Theia impactor? Each hypothesis has strengths and weaknesses. Resolving this question will require better seismic imaging, more sophisticated geodynamic modeling, and perhaps direct sampling through analysis of plume-derived volcanic rocks that might carry signatures of LSVP material. There are also questions about what drives plate tectonics. Is it primarily the pull of cold, dense slabs sinking into the mantle? Is it the push from mid-ocean ridges where new crust forms? Is it convection in the mantle dragging the plates? Most likely it's a combination of all these, but the relative importance is still unclear. Understanding the forces that move plates is essential for understanding Earth's tectonic history and future. The relationship between the surface and deep interior is another area of investigation. Geochemists find that volcanic rocks from ocean islands have isotopic signatures, suggesting they sample ancient, primitive mantle material. But where is this material stored? Is it in the LSVPS? Is it scattered throughout the deep mantle? How has it avoided being mixed by billions of years of convection? These questions touch on fundamental issues of how Earth recycles and stores materials. The future of Earth's magnetic field is uncertain. We know the field reverses irregularly. We know the field is currently weakening, about 10% over the past 170 years. Is this the start of a reversal, or just a normal fluctuation? Will the field weaken further, exposing the surface to more solar radiation? Predicting magnetic field behavior requires understanding the geodynamo better, which requires understanding the outer core better. Earth science is entering a golden age. New satellites are providing unprecedented data on gravity, magnetic fields, and surface deformation. New seismic networks, including ocean bottom seismometers, are improving coverage of previously undersampled regions. New laboratory techniques are pushing experimental conditions closer to those of Earth's deep interior. New computational models are simulating the planet with increasing realism. All these advances are revealing details of Earth's interior that earlier generations could only dream about. But there are limits. We will likely never directly sample the lower mantle or core. We will likely never observe the geodynamo in action. We'll never watch mantle convection happen in real time. Our knowledge will always be indirect, inferred from surface measurements and theoretical models. Yet the progress over the past century has been astonishing. From barely knowing that Earth has a core, to mapping the inner core's rotation and shape changes. From thinking the mantle was solid and immobile, to understanding its convective patterns. From assuming Earth's interior was dry, to discovering oceans worth of water hidden in minerals. The journey of discovery continues. Each new observation refines our understanding. Each new experiment reveals unexpected details. Each new model makes predictions that can be tested. The interior of our planet remains, in many ways, one of the final frontiers of exploration. You might wonder why any of this matters. Why should we care about what's happening thousands of miles beneath our feet, in realms we'll never see, under conditions we can barely imagine? The answer is that everything about Earth's surface, everything that makes our planet habitable, is intimately connected to its interior. Plate tectonics, the process that shapes continents, builds mountains, and creates oceans, is driven by mantle convection. Without the heat engine of the interior, there would be no tectonic activity. Earth would be a dead world with a static surface, like Mars or the Moon. The continual recycling of crust, the subduction of old ocean floor and creation of new, the collision of plates that builds mountain ranges, all of these are surface expressions of convective processes in the mantle. Earth's magnetic field, generated by the geodynamo in the outer core, is our shield against the solar wind. Without it, high-energy particles from the sun would strip away the atmosphere over geological time. Mars lost its magnetic field early in its history, and its atmosphere was gradually eroded by solar wind until only a thin remnant remained. Earth's magnetic field has protected our atmosphere, our water, and by extension, life itself. Volcanism brings material and heat from the interior to the surface. Volcanic gases, released during eruptions, contributed to the formation of Earth's early atmosphere and oceans. Even today, volcanism releases carbon dioxide, water vapor, sulfur compounds, and other gases. Over geological time, the balance between volcanic outgassing and weathering processes regulates Earth's climate. Without volcanic activity, Earth's carbon cycle would shut down and the planet would freeze. The water hidden in the mantle is part of Earth's long-term water budget. Water subducted into the mantle can be stored for millions or billions of years before being returned to the surface through volcanic activity. This deep water cycle affects plate tectonics by lowering the viscosity of mantle rock and facilitating subduction. It affects volcanism by lowering melting temperatures. Understanding how water moves between the surface and interior is crucial for understanding Earth's evolution. The heat flowing from Earth's interior powers geothermal energy systems. In places like Iceland, New Zealand, and parts of the western United States, this heat can be harnessed to generate electricity. While geothermal is a small fraction of global energy production, it's a clean, renewable source that will last as long as Earth's interior remains hot. Earthquakes, which pose hazards to billions of people, are surface expressions of processes in the crust and upper mantle. Understanding how stress accumulates on faults, how subducting slabs interact with the overlying plate, how the mantle responds to tectonic forces, All of this helps us assess earthquake hazards and potentially forecast large events. Climate change over geological timescales is influenced by processes in the interior. The amount of carbon dioxide in the atmosphere is regulated by a balance between volcanic outgassing and weathering of rocks. On timescales of millions of years, changes in tectonic activity can affect climate. Periods of extensive volcanism can warm the planet. Periods of mountain building can cool it through enhanced weathering. Understanding Earth's climate history requires understanding the dynamics of the interior. The origin of life might be connected to Earth's interior. Hydrothermal vents on the ocean floor, where hot, mineral-rich water emerges from beneath the crust, are thought by some scientists to be potential sites where life originated. These vents exist because of Earth's internal heat. The chemicals dissolved in the hot water, the energy gradients available, the protected environments, all might have been crucial for the emergence of the first living cells. Earth is unique in our solar system in having active plate tectonics, a strong magnetic field, abundant liquid water, and a temperate climate suitable for life. All of these are ultimately consequences of what's happening in the interior. The heat, the convection, the geodynamo, the cycling of materials. They're all interconnected parts of a system that has kept Earth dynamic and habitable for over 4 billion years. When we study Earth's interior, we're not just satisfying curiosity, though that alone would be justification enough. We're learning how planets work. We're understanding the conditions that make a world habitable. And as we discover exoplanets orbiting other stars, as we search for signs of life beyond Earth, the lessons we learn from our own planet's interior inform that search. We know what to look for. We know what conditions are necessary. Earth is our laboratory, and its hidden depths are textbooks in planetary science. So there you have it, the journey from surface to center. From the thin, fragile crust, we walk on to the churning mantle beneath. From the liquid iron ocean of the outer core to the solid crystal ball of the inner core at Earth's heart, a journey of nearly 4,000 miles, through realms of increasing pressure, temperature, and strangeness. A journey we can never physically make, but can reconstruct through science, observation, and reasoning. What's hiding inside the Earth? Oceans of water bound in minerals, ancient structures billions of years old, witnesses to Earth's earliest days, minerals that exist nowhere else in the solar system, a dynamo generating the magnetic field that protects us. Convection currents moving rock at the pace of fingernail growth, but reshaping continents over geological time. Heat from the planet's formation, still radiating outward after 4.5 billion years. The interior of Earth is not some static, unchanging foundation. It's dynamic, evolving, complex. The inner core rotates and changes shape. The outer core churns and generates our magnetic shield. The mantle convects, transporting heat and driving the motions of tectonic plates. The LLSVPS sit at the base of the mantle, massive and mysterious. Water cycles between surface and depths, lubricating tectonics and feeding volcanism. All of these processes are ongoing right now as you read these words. We've come a long way from the early geologists who thought Earth might be hollow or filled with fire, or unchanging since creation. We've learned to read the subtle signals the planet sends us, the vibrations of earthquakes, the pull of gravity, the measurements of magnetism, the chemistry of volcanic rocks. From these clues, we've assembled a picture of a world within a world, hidden but no longer entirely secret. Yet mysteries remain. We don't fully understand the LLSVPS. We don't know exactly how the geodynamo works. We don't know why the inner core's rotation has changed. We don't know how much water is in the mantle or how it got there. We don't know if there are other structures, other anomalies, waiting to be discovered in the depths. This is the beauty of science. We've learned so much, but every answer opens new questions. The frontier moves inward and outward and deeper into the details of what we thought we understood. Earth's interior remains one of the most challenging and rewarding subjects of study in all of science. So the next time you feel the solid ground beneath your feet, remember what lies below. A thin shell of rock barely scratching the surface, then thousands of miles of slowly flowing solid rock, convecting, churning, moving tectonic plates. Beneath that, an ocean of liquid metal generating our magnetic field. And at the very center, a solid sphere of crystalline iron, rotating, changing, growing. All of it hidden, all of it essential to the world we know. This is our planet, not just the surface we inhabit, but the hidden depths that make that surface possible. From the crust to the core, Earth is a complex, dynamic, interconnected system, and we're only beginning to understand it. If you enjoyed this journey into the unknown depths of our planet, please take a moment to hit that like button. Subscribe to the channel to join me on more explorations of the cosmos and the mysteries of our universe. Until next time, keep looking up at the stars, but don't forget to wonder what lies beneath your feet as well. Thank you for watching.